Okay, today we're going to implement the backprop. And I'm going to check with everyone in terms of the theory last week. Were there any questions over the past 2 weeks? All good? Okay. All right, so then today we will just assume that all the theory and concepts are relatively okay. And then we're going to see how to actually do it in a code. Before that, I'm going to run through some pseudocode. So like just tell you about the sequences of what the code later will, what you will need in the code or why we do certain things in the code. Okay, but just to get you in terms of the overall framework and the approach that we're going to be adopting. So still a little bit of kind of conceptual level first before we jump to the actual code. And by way of the notes, these notes are all on the course NTU Cool, right? All the blackboards and all that. But I'm just going to go through them again, kind of step by step. So, you know, otherwise maybe sometimes the notes are like, it jumps too far ahead. Okay, and then after that, the the Google Colab notebook is also there. And we will go through that today. So you can open it up and follow along if you want to, but we will get to that later on in this course, in this class today. Okay, so the first things first is that we want to implement the backprop. So what is the pseudocode or the framework? So today we will be doing backprop implementation. And as always, I remind ourselves that the goal here is to kind of answer the research question or the simulation question. How do we make a network, okay, map any input to any output, okay? And the idea from the Hinton work or the Rumelhart work is that you can do that through using the delta learning, which is that you have some output, you compare it to some target desired output, and this difference, which we call delta or error, has a form in the formulation from last week. It has some relation to the function of the activation function, which we will see, right? It's the derivative of the sigmoid function, modulating that error, okay, and then backpropagating that back into the rest of the network and changing the weights according to that error. Doing that, we'll do gradient descent in terms of the error will be minimized, okay? From whatever error it is, okay, it will become 0 or has the slope direction towards 0. And so in doing that, you can theoretically map anything to anything, okay? So the implementation, first thing we need to do is always to specify the architecture. And in specifically, we're going to specify a multi-layer perceptron, MLP architecture. Okay, and we did this already last week. So for example, we might have a 10 input units, 8 hidden layer units, and then 4 output units, okay? And, or you could have something more complicated, you know, 10, 4, 10, 4, you can do it whatever you want, however many hidden layers you want, and how many units per layer that you want, all right? These are all up to the simulation. In the tutorials, assignment 2 that you will be doing, there's certain instruction that you have to limit your framework or your architecture. But in broader application, if you can feel free to do it, you know, however many ways you want. It is really a matter of does that network solve the problems that you need, okay? And using vector notation, for example, the 10, 8, 4 might look something like that, all right? And then you have the input units, hidden units, and the output units. And then correspondingly, you have your weights, all right? And we call this a feed-forward, fully connected 10-8-4 network, okay? So you specify whatever architecture you have, like this. Not really that difficult. Then you do the learning rule. You have to specify the learning rule. And as we talked about, before, the learning rule in this case that is implemented for now, other networks, they will have many other learning rules, right? For example, the Hopfield network had its own learning rule. In the case of this exercise, we will use the learning rule that has the stipulation that the weights, Ji, backprop, by the way, okay, not I to J, but J to I, okay, in terms of the weights that are changing according to the error, according to what is being learned, okay, are the backward weights at the time that is later on, okay, the next iteration is going to be equals to eta, which is the learning rate, okay, learning what is new, new learning, okay, how do you say, the weight or the proportion, okay, of new learning that we want, which is eta, and the delta from the output layer for state S as a function of the input that created this error, okay, plus the momentum, the weight of old learning, right? So to the extent that the previous change in weights hold back the proportion of the new weights, all right? And in this case, we have, I believe we made it such that, yeah. Sorry, it cannot be equals, otherwise it will, well, you can, but then it will be, not really that meaningful. These are the qualifications, the conditions, the parameters that have a hard limit, some constraints, okay? Again, this is in the implementation we are going to do in class. If you go into the broader, literature, of course, things might be different, but just when you see this implementation, the important thing is you know what it means when we do it our way in class this way. If you change it, well, then you're free to change it, but then know that what that means in your case, okay? All right, then after we have the learning rule, we're going to specify the activation function. And again, similarly, this is what we will use in this course, in this class for this network, but other instances might use other activation functions. And as always, the activation function is going to be, if we remember the perceptron, so the perceptron has this part will give you, right, the pre-activation state, all right? You sum all the products of the input by their respective connection weights. And then this is really the F here is this, right? Is you take that pre-activation state and then you apply a nonlinear function. That's why you have that step function there. Not that it will be a step function, but it is a symbolizes that it's a nonlinear application, all right? And so we have a F of the pre-activation states. To be, and then applying the nonlinear function, it becomes the activation. And what is this nonlinear function that we're going to use? As I said before in this class, we're going to use the sigmoid function, which is going to be e exponential of, I'm going to use shorthand, okay, which is going to look like this, all right? And so, in fact, what this means is that it looks like this, right? Okay, so it's going to be asymptote. It will never really reach 1, and it will never really reach 0, but it will get closer and closer to it. The key thing is that within some range around theta, there is a step or a continuous sudden shift from 0 to 1 kind of activity. So that's the sigmoid function that we will be using. And importantly also, note, because this will become important later, we will also need the first derivative of the activation function. Okay? And specifically, if you work it out, I put up the proof in the announcement or the notes from last lecture, and it turned out that it should be aj 1 minus aj, if you work it out. Okay? It's a very straightforward proof, so you can take a look at it. But the point, we need this because if you go back to last lecture, we talked about how when you come to the hidden weights, right, we don't know how to adjust the hidden weights in terms of, unlike the final output, in terms of the hidden layer error, we don't know how to adjust the hidden layer errors compared to the final output error, which is very straightforward, right? So it turned out that we can use this derivative to adjust that internal hidden errors. Again, you have to go back to the lectures a couple of weeks ago to revise the details. I won't go through that today unless people ask offline later, okay, for interest of time. But we will need that, okay, for that reason. And it will become clearer as you implement it, you'll see. Okay, so we have all those components: architecture, learning rule, activation function, and a little bit other details, right? And then it remains to us to apply the architecture, the learning rule, and the activation function. Okay? And in other words, we establish a pipeline, pipeline code. And in terms of pseudocode, what we are going to do, when we have those components, the first thing we're going to do with the component is we're going to have a feed-forward phase. Okay? What this means is that pseudocode, okay, for every input, for every hidden layer, and for every output, in whatever size of the architecture, which is determined by the big W, okay, all the weights, every layer, okay, that's big W. That's just the dimensionality. The size meaning the number of layers that you have, okay, so this is pseudocode, okay. We are going to make it such that the AJ, in this case AJ is not the final output, but the downstream layer output, okay. Every layer's AJ, okay, so this is going to be like every layer. For every layer, the downstream output is going to be equals to the function the application of the activation function, which is equals to 1 plus E WAI plus theta inverse. This is the sigmoid function, just expressed in a slightly different way, negative, okay? All right, so in the feed-forward phase, for every layer, we are going to make the downstream layer's activity equals to the upstream layer's products of their activity with their weights, applying the sigmoid function. Not very difficult to understand, but you have to be clear that that's what we're going to do first, okay? Simple. Then, after we do that, so this is feed-forward phase, which is forward propagation. Okay, after we've done that, we will then calculate the error at output. okay? And this is going to be theta, let's call it theta j. And according to the framework that we're using, obviously there's going to be the difference between the actual output, which is AJ, minus the target output, which is AT, okay? All right there? And then but that's not enough. We're going to have to, because this is a non-linear case. So if it is linear, then it's just that. Because if it's linear, f is 1, right? The big function, activation function, is a slope of 1. That's a linear case. In the non-linear case, we have an activation function that's non-linear, the sigmoid function, and it is the derivative of it that we will adjust it by, okay? So this is, as you can see, right? So you apply the derivative function and adjust the difference, okay? Let's call this E, or whatever you want to call it. And the result is the actual delta that we are going to use to adjust all our backprop weights later on. But first we compute the delta at output, all right? So then when you have this quantity, after you have this quantity, then you do the backprop. The calculated delta, okay, to the learning rule, remember, which is the changes of j to I weights, okay? So just to remind ourselves again, AI is upstream activity. Yeah, and then momentum, okay? So it will look like this. We have input. We do forward propagation of the activity, okay? Like this. Sorry, we don't, that's just the weights, so we don't need the I here. The AI is there already, okay? And then we have the A prime J, which is the pre-activation state, okay? And then we apply the sigmoid function, which is the 1 over 1 plus E minus, let me use the shorthand. Okay. That is AJ, okay? Correct? Oh, let's not use circle. Let's keep it to the vector notation, okay? Actually, this is a bit confusing. So I'm going to just, because that assumes that there's another layer. No, I'm just going to make this that this is AJ, right? Okay? I mean, that's the actual thing. Then we're going to compute delta J, which is going to be a vector, right? Because every unit of J unit will have its own delta, which is going to be equals to AT minus AJ vectors, okay? Vectors, right? Okay? And then this quantity okay, is going to be used. So this is 1, this is 2, and this is step 3. This quantity is going to be used to calculate. I'm going to reiterate it again and again. So we are very clear because the coding is going to be a nightmare. Okay. Okay, we're going to apply that And just so you know the dimensionality, okay, this is going to be K by R, and this is going to, and therefore this also has to be K by R, right? The weights has to be K by R, because the weights are going to be K by R, okay? In terms of every upstream, downstream layer dimensionality, the array, the W array will have to coordinate that kind of dimensionality. It's important or helpful to know the dimensionalities because then you know your setup makes sense. I'm just putting this out here now. Don't worry if you don't know what K, what R. It will become clear when you actually implement the code. I'm just raising that you have to start considering this as a vector, an array, output a vector, and then the delta is a vector, and then you're backpropagating these vectors into the weights arrays, and so on and so forth. Okay? So 1, 2, 3, 1, 2, 3, 1, 2, 3 all the time. That's what the code is going to do. Okay? Let me draw it out another way. So this is AI K equals to 1. Okay, AI 2, AI 3, AI 4. Okay, so these are K units, K by 1, or 1 by K, all right? And if I assume no hidden layers, JR1, AJR2, all right? R, okay, where R is, this is R, okay? R1, R2. And so then I have K, because this is I to J, right? So this is K by R, that's what, okay? And so right? And so this thing has to be used to adjust the weights, and so it has to also be sort of projected back into a K by R kind of dimensionality. Okay, so this is just a sidetrack to help you to visualize the vector notation way, the conceptual pseudocode way, the vector notation way, and then which then brings us to the dimensionality closer to the implementation level. And then if you still find it hard to visualize, well, you draw out the units and then you count, you know, and you'll see how it all fits. Okay? All right? Okay, so let's see here. All right, so this is, if we assume we have no hidden layer, our delta is a AT minus AJ times the first derivative of the sigmoid function. Okay, but what if we have a hidden layer? Okay, in terms of the hidden layer, I'm going to draw this out again. Let's say we have a hidden layer with 2 units, and then let's say we have AJ with 3 units. Okay, so we're going to make this go this way. It's AI, AH layer, and AJ layer. Okay. So at the final output, we're going to have a delta, which is AJ minus AT, AJ, sorry, AJ 1 minus AJ. Okay, that's the delta. So then we use this to change, I'm going to change color. This is going to change backprop the weights here, so that this is equals to the epsilon delta J, right? This one. Actually, let me be very specific. This goes here, right? And this is AI. This goes here, right? Okay, plus the momentum. So that this, sorry about the crisscross, but okay. Okay, when we change the weights of Wji at the final output layer, those are the components. The delta J comes from the output, delta J. The AJ, or in actually it's AI, right? But because, yeah. I'm sorry, this is a bit confusing. Let me write it very clearly so that it's not confusing. AI is actually AH, right? Because it's the upstream input, okay? So that gets put into this AI part. This is the AH, but it becomes the AI for that part because it's the relative relationship, plus the momentum adjusting the previous weight change information, okay? So that is for this output layer, okay? But what about here, okay? What about here? Okay, what is the delta? And in this case, we need the delta H. So we need to know this is going to have a W. This is Wji. I'm going to call this WH. Okay, just to be very clear. So this is JH, okay? And this is HI, right? Because this is the I layer, and this is the HH layer, okay? So WHI is going to be also having the eta here, okay? But what is this delta? It's going to need a delta H. And obviously, whoa. And obviously, it also has the AI plus epsilon. Okay, so then let me change colors one more time. What is this quantity? Okay, it's going to be equals to, let me write it where there's more space. Oops. Okay. Yep. The activity of the hidden unit, 1 minus the activity of the hidden unit. So this is the derivative function. Okay. The derivative of the sigmoid function part, okay? And it's going to adjust the, I don't want the symbol because I know that this is a vector, okay, of the J, J. WJH, yep. At time t. Correct. Okay, what this means is that the delta J is the backprop from the output layer, right? The delta from the output layer. And you adjust it by the weights at the previous time. Sorry, not this one, but this one. Okay? In other words, what caused this error was the weights previously. at the output layer that cause this error. So you adjust, you down regulate or you regulate the error from the output layer by the weights that cause that error, then that quantity is then applied to the derivative of the sigmoid function for the h, okay, for the h. Why does it always do that? Okay, and then that becomes the delta H that will be used for the hidden layers weights adjustment. Okay, so we have to do this distinction. There is a layer, output layers delta, and you use that for the output layer weights adjustments. Then as you go deeper than that, you will have to adjust the weights accordingly by the weights of the downstream error adjusted by the downstream weights, and then feeding back into the derivative function. Then you get the delta of that layer, and then you can use that for the weights. So you can really see that it is really a propagation because every step is a kind of a wrapper around the previous step. Correct? We did that in the last week's lecture. You saw that really essentially this MLP is a function of a function of a function. It's a wrapping all right from the start all the way to the output. So similarly, this delta is a function of a function of the function because you are wrapping all the final output back into however many layers you have there. That's how this is done. Okay? All right, so we have the case where, if I go backtrack a bit, this is the sort of the pseudocode thinking without the hidden layer for simplicity first. You do step 1, 2, 3, okay? Feed forward, calculate error, and then backprop the error, okay? And in the case of the output layer, it's simple because the delta J is this function. But in terms of if we have hidden layers, it's not just so-called 1, 2, 3. It is 1, 2, and then the 2 is like it depends on which layer you are, and then you apply 3. Okay? So in our pseudocode, you will see we will have to have a code part for the output layer and a code part for the hidden layers as well. Okay? If you're very savvy with coding, if you really understand things, you might be able to squash all that into one line. I'm not sure. Okay, yeah, very much welcome to do that if you want to. Okay, any questions about this, the pseudocode implementation? All right. Then one last thing we have to talk about is the issue of bias. Adding bias units, okay? Okay. What does this mean? I will first tell you how we add the bias units, and then tell you why we add the bias units, okay? What bias units means is that assume that we have AI, which is 1 to 4, like this, okay? And they are connected to AH, and they're finally connected to AJ. Bias units means, so inside because we're talking about units, bias units means we have bias like this. And it will have its weights. Let's call this B, okay? But it's basically just one more weight to H, and it will have HB to J, okay? And the activation of the bias units is always equals to 1. The ith layer by so let's make it so that it's not so complicated. Okay, so the bias unit is always set to having an activation state of 1, always 1. It has its weights that will be part of the feed forward. So it's always feed forward. Okay. And importantly, there is no, how do I write it? There is no change in the bias weights. I have to write it by J to IB. Yeah, okay? There is no learning of the bias weights. There is only feed forward of the bias weights, but the bias weights don't get adjusted according to error. Okay, we do it this way, but it does affect the feed forward. So in other words, what it does is effectively it's a normalization. Okay, it doesn't learn. It doesn't get like pulled back and forth. Okay, it just sets a particular mean, which is what it is, okay? It sets a particular baseline about which all the other weights are made relative to the bias weight. Okay? Let me write it in another way and you will see how it is clear. Because if we see this part, if you just take this part, and you appreciate this equation, you will see how it works. Simply put, yeah, okay? The AJ vector, right, is going to be equals to this. No, sorry, there is no vector here. It is just AB times its weight, right? So AJ. And we know, because A is always set to 1, AB is always set to 1, so it is whatever W is, WB is, right? And it's a constant, isn't it? With respect to AJ, it's a constant. It doesn't change. It is an intercept. So in which case, recall general linear model, where y equals to ax plus b. It is the intercept. Okay? So in a general linear model, the intercept is when x is 0, or whatever x is constant level. And then all the other variables, the line must be anchored at intercept, and then it has its slope, right? That's GLM, correct? Okay? So it's important in GLM that you must anchor your slope. Otherwise, your slope can go all over the place and you cannot solve, or it explodes. Okay? The equation falls apart. the key concept of GRM, the very basic simple linear regression, is you have an intercept, you anchor the whole function, and around this agreed first starting point, you can vary your slope, the AX. Oh, sorry, don't, because you use A all the time. Let's use beta coefficient, right? Like that. Okay? So it's a normalization, or specifically speaking, it is a regularization, rather. We impose, we regulate the weights so they don't have infinity to play with. They have a constraint, and the constraint is that it must be anchored to the equation's agreed intercept point. Okay? Means the numbers of the slope cannot go from, are not free to vary. There is a constraint which -1 degree of freedom, basically. That's what that means. Okay? So the bias units in the network do that. Why? Because if you don't, and you let the delta keep changing all the WIHs, okay, without any anchor points, your model will explode or never converge or whatever it is. It will basically not work. So or it will work, but it may work, but then it doesn't really actually solve anything. Okay, all right. So that's the regularization we have to implement. Okay, so this bias units, we have to introduce this as well, and that's how they work. Okay, the idea of normalization will come in again in the last model that we will use, which is the von der Waals model. Okay, but that regularization or normalization is a different way of implementing. And as I said, there's many different ways of normalizing and regularizing. Okay, this is just one way, by introducing bias weights. All right. So just like you have different learning functions, you have different architecture, different activation functions, you also have different regularization functions or methods. This is one of them. Okay, so this is the implementation. And we're going to actually go to the code next. Any questions about the pseudo-code concepts in terms of implementation? All right, so then we're going to try out the Google Colab code. Shall we take a 5-minute break? Okay, then we come back and then we will take a look at the code proper. If you want to, you can open the code up yourself. It's from the NTU Cool. You can see the Colab link. And then in 5 minutes, we come back and then we'll start dealing with the code directly. Okay. back. Before I jump into this, I just want to get a feeling of how people are with the hot fields assignment. Is that okay? All okay? All right. This is important because we are going to go into the backprop assignment, right? And traditionally, if you get lost at the hot field, and then now I'm talking about the backprop assignment, people get confused as to like which assignment, and then they get stuck and all that. Okay. So it's important that, and we have to do it this way because you are working at the hot field, but at the same time the lecture is moving forward with the next thing. So you have to be very clear that it's kind of like sort of in parallel, all right? But then there's a risk of things getting confused, right? So just to make sure that everyone is okay with the hot field assignment, and because you will see elements of that it's overlapping and it's almost similar in the format, okay? That can be good for some people, but it can also be bad for some people, okay? Because you will see the common things, and then you see, oh yeah, it's the same thing, but then I change certain things, and then I can do different things, all right? But to some people, that becomes a confusion, because maybe there is some critical thing not yet figured out, okay? So but that's what we're trying to do here, is to show you the similar approach and framework, and we just recurrently, iteratively apply it. And hopefully the idea is you see that it's the same thing in the bigger framework. It's just we tweak certain components and then we achieve different goals, okay? All right, so everyone seems to be okay with the hot field, so then I'm relaxed about that. So let's talk about the MLP implementation of error backpropagation. So just again, the final goal for this course, at least for the backprop, is that you can do assignment 2. So you can see assignment 2, I've made it open. And you will see that assignment 2, again, disclaimer, all this work, the fundamentals of it, is from when I learned it when I was in Illinois. I've adapted it, this is not the original form, but the core of it has always been from there, okay? But so, in the assignment, should be assignment 2, not 3, so let me change that, sorry. 2. Okay. It is due on June 5th, which will be the date where I start the von der Mausburg network. And the von der Mausburg network will be due a few weeks after that. Okay? But so you will see it's similar to the hot field approach, which is that I give you some input training sets, and then you test it. Can the model learn these sets of training patterns to be different outputs and into different outputs? So you will ask, hey, where are the outputs here? Well, these are different tokens, input tokens, but you will see that we are calling the first to category A, second to category B, and so on and so forth. So in other words, the outputs are A, B, C, and D, so that this pattern and this pattern should be mapped to, let's say, 1, 0, 0, 0, okay? And then this pattern and this pattern should be mapped to 0, 1, 0, 0. And then this one and this one should be mapped to 0, 0, 1, 0, right? So that's what this means, okay? You're mapping these into, these are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Is it 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 10. 10-bit words, mapping 10-bit words to 4-bit words, for example, okay? All right. So you will see this is a pretty similar setup, and that's the goal that we are trying to get you to. And we will be using this coding format. Again, feel free to do it however way you want it. This is my Colab instantiation of it. And in so doing also, we have a sort of a tutorial, revise the concepts here. So remind ourselves, the goal here is to implement a MLP that learns using backprop and learn what? Well, we learn how to map whatever input to whatever output, okay? And in this case, I talk about token mappings, which is mapping some token to some other token. And we talked about tokens a few weeks ago. You know, I always say about stimuli, feature, or n-bit words or whatever. Essentially what we're talking about is tokens, but the idea of tokens is a little bit more abstract. Tokens does not mean that the way we encode things. Tokens mean the way the machine receives some input and then causing it to have all sorts of implementations or operations subsequently. All right, that's token. Okay, so we define the problem. It's important to always come back to center yourself and then like formalize what you are trying to do and remind yourselves of your goal. So the primary challenge is that we want to test whether a neural network can be taught to encode anything to map to anything. This is the overarching question. Can a neural network do this in the first place? Okay? You always have to convince the reader that you have a legitimate research question. Any exercise, academic exercise you do, has to come from like, what's the question in the first place? And is this question meaningful? Is it worth asking? Okay? So this is the question. We are assuming neural networks can do all this because we live in AI world. Everything is now, you know, we're in 2026. But push yourself back to 1960s, okay? No computer, not everyone has a computer, let alone a cell phone, a mobile phone, right? So the idea that you can have this neural network and this neural network can do anything is actually pretty amazing, isn't it, right? So you have to think of things that way, okay? Put yourself in that frame. So we start from the very fundamental question in the first place. Assuming we don't really know, we don't have all this experience, how do we know that a neural network can actually solve such problems, right? So this is a legitimate research question. Well, the solution is, well, let's try it. Let's make a neural network, and what we mean by neural network with the architecture, activation function, etc. And then let's see if it can solve such problems. If it can, then yes, the answer to this question, this challenge is yes. If it cannot, then the answer is, at least according to our setup, no, it doesn't seem to be able to work. Okay, so we have this research question and we're gonna try to answer it. So this includes mappings that are nonlinear, involve multiple units, blah, 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 all sorts of inputs to all sorts of output mappings, okay? And the critical thing is to evaluate a loss function. That is what we mean by when we want a neural network to solve it, we want it to minimize this loss function, okay? And theoretical basis is from a few weeks ago. So that you train the weights and it does gradient descent, and in gradient descent, we minimize the loss, and so therefore it can solve those problems, all right? And then obviously this is Hinton's work, blah, blah, blah. Okay, and the references. And I have the GitLab. Oh, it's GitLab. I didn't put in GitHub. Let me give me a quick check. Oh, it's my GitLab. Oh, okay. I actually have a GitHub on it. Maybe I'll update it later. All right, doesn't matter. It's the same thing. So anyway, so you can go check out if you want in terms of the Git. Okay, so this is the data table. We always start by framing the data table from the formal concept. We then come to the concrete problem, which is to solve this data table. And as I said before, let's say we have this category A, category B, category C, category D. So this is essentially assignment 2, part 1. All right? So that's what I'm trying to do here. So solve this data table. If you give input tokens like this, can it generate output tokens like this? Okay? So let's visualize this. And I have this code here at first, which is the prompt I use. Use Plotly because I like Plotly. You can use anything else you want. And plot the table above as heat maps in 2 subplots, blah, blah, blah. Okay? So if you follow this code, sorry, here. Okay, this is too big, so. Oh. Can you see? Okay, all right. Okay, just to visualize the data table, which is that I want these two rows to be equals to these two rows, correct? And these next two rows to be this next two rows. So I want to be able to, and so for those of you who are very good at mathematics, this is very abstract, but it's very profound. Essentially what neural networks are doing is transforming this array, this dimension, into another array basis, okay? So it's actually a rotation, all right? This array, make it look like this array, and using some intermediate function, right? That is the same as array, matrix to matrix rotation. Anyway, mathematical sidestep. But essentially what we are trying to do is to map this one to this one, okay? So that's the visualization, nothing fancy there. It's the data table, but just making it like look cool, that's all. And the hypothesis, given that data table, the hypothesis is that we can, in order to solve this mapping, in order to achieve that mapping, we can use an MLP, multi-layer perceptron, which can learn anything to anything. Because, so going back to the very early lecture, when we have a single layer perceptron can map linear problems, right? And logic table or logic tables. But when we try to use XOR or anything else that require nonlinear mappings, okay, single layer perceptrons break down. But we found that if you tried it also, if we did a hidden layer, we add one more layer in it, then it could solve the XOR. So it became that single layer perceptrons cannot, but multi-layer perceptrons can solve nonlinear mappings and can solve linear mappings as well. So both linear and nonlinear ones, what other sort of mappings are there? Pretty much that's all the mappings there are. So everything, right? So in other words, there's a legitimate hypothesis here, a well-motivated one, that an MLP can do what we want it to do for the data table. So we make an MLP that takes 10 input units, because our mapping here is 10, okay, 0 to 9, okay. The inputs are 10-bit vectors, right, 10-bit words, and produce 4-bit outputs, 0 to 3, okay. And with any architecture hidden layers, blah, blah, blah. Okay, so make the network space update based on the error of the network's output and the target output. Okay, this is the AT, the target output. Okay, this is the AI, the input. Okay, so the code works like this. First, we will need NumPy, as usual. We need some SciPy tools as well, you'll see later on, because what this will be important for is the sigmoid function. Okay, SciPy has a nice sigmoid function that we will use. But if you want, you can do the equation yourself. 1 over 1 plus e to the power of the weights, okay, the pre-activation state. But I'm just using, this is the only cheat I have, so to speak, without the mathematics, because, well, there's nothing fancy about it. It's just that there's a nice exponential sigmoid function that we can use, okay? And then some plotting tools, matplotlib. And the first function or definition that I will define is the one that will actually train first, okay? Which is, in this definition, let me skip the comments. You can read the comments, the help in front, but just taking a look at the code. I have a function that I call trainNet perceptron. So I want to train this multi-layer perceptron. And this training can take a set of input arrays, W, okay? This can be from already trained one, pre-trained one, or it can be a fresh one, okay? So it will take whatever input if you have, So whatever weights, connection weights if you have, it will also require obviously the input you want it to be trained on and the desired output, D out, that you want it to be trained to produce, okay? And then I have this where I want to give it some more information about the architecture, like the number of layers and the units in each layer. And then some other hyperparameters, epochs, which is the number of iterations, okay? The error, some threshold minimum where I reach in terms of the gradient descent, where I satisfied that it's not going to descend anymore, then I stop, okay? So I need that. And then eta and mu, which are the learning rates and momentum in the equation, all right? If you want to see more details, obviously the help there does define some of this, all right? But those are the component inputs that this trainnet function requires, okay? So how do we do that? First, we remember the training. Training means we are going to have a set of weights, W, and the weights are going to change, the change in weights. And the change in weights occurs by the backprop algorithm. So in other words, we're going to do the actual whole step 1, 2, 3, feed forward, learn delta, backprop, change the weights. This is the training part. We're going to actually do the training now, okay? So go back to just now the pseudocode. What do we do? The first thing we do actually is to add the bias units. So if I can skip back, this one. All right, although we do 1, 2, 3, which is the basic core loop, in terms of the operation, the first thing we actually have to do is to make it such that we have bias units. Okay, so that's what the code does. Do bias units first, which is that for whatever input size that we have, so let's say we have an input is 10-bit words, right? If we add a bias unit, it becomes an 11-bit word, correct? With the 11th unit always having an activation of 1, okay? So that's why we have to add the bias units. So, and the bias units have to be done for every layer, okay? So whatever number of layers I have, I am going to make whatever original number of units, I'm just going to increase the number of units by 1. That's the bias unit, okay? So I set that up first. Then I initialize the connection weights, W, all right? And I have to have some hold patterns and W's. You see I have all these placeholders. It's because you will find that you need time t plus 1 and time t, correct? You want to hold something, but you want to update it, but you may not want to apply it yet. So you need to have at the same time both weights so that you can hold this, calculate this, then calculate something else, and calculate something else, and then when you're ready, then you apply it, all right? Because if you don't do it, once you apply it and you want to calculate something, you've lost the original things, you can't calculate it anymore. So you have to split this like this for this reason. So you have the hold pattern and the original pattern, okay? And we set it up, let's say you don't have anything, you don't have any pre-trained networks, so you just want to set up a fresh network. The fresh network starts with an empty array, okay? So W equals to empty, okay? And the whole pattern also empty. And we initialize it with random uniform numbers ranging from -1 to 1 first. If you don't have any pre-trained network, well, the initial start would be any random, a network W that's filled with -1 to 1 range of random numbers, okay? All right, so that's what this random uniform does. And you will note that it doesn't have to be integer. It can be any decimal float number, okay? Random uniform, as long as it's uniform and it's -1 to 1. And the holding weights, I'm going to just set it up to be 0 first, okay? An array of zeros. So the initial weights, which is, again, you see HW here, okay? It's not W. I haven't applied it yet, but I'm just going to calculate some other things as a random random set of numbers, okay? So, and I do this for each layer, okay? And then I remove the connection to the next layer bias unit, Okay, so I only want the units, bias unit. This works, right? Yeah, okay. Okay, so here, I have the bias unit connects to the next layer. So I only have WIBH, okay? But I do not have, so for this layer and this connects forward, right? I do not have a connection from WI to the bias unit. Okay, so that's what this means. Removing the previous layer's units connection downstream to the next downstream bias unit. There is no such connection. Bias units are always connection to its downstream, but it does not have an upstream connection from the upstream units. Okay, so that's what this does. And just set it up, and then that's it. And you do this for all layers. All right. Okay. So this is in the case where there is when W is none, nothing, no pre-trained network. If there is a pre-trained network, don't need to set up W, just create a whole pattern and set up the zeros, and also remove the bias unit previous connections and all that. All right. So this is all just to initialize W. In the case where you don't have a pre-trained W, then set up W as a random array -1 to 1. Okay. If you have a pre-trained one, okay, we can use that, but then we still have to set up the other holding patterns, dimensionalities, and connections accordingly. Okay, so that's what this line up to line 79 does. Then now we are ready. We have set up the weights architecture. So actually, all the way to line 79 is actually the architecture part. Setting up the weights in terms of how many weights we want and for which layer, and then are there bias units and how the bias units are connected or not connected. All this is setting up the architecture. Okay, so this is W initialization is actually equivalent to architecture setting up. Okay, now we do the feed forward part. And you will see, we first have an outer loop, which is a wrapper to stop how many epochs we want to run. Okay, so when we want to run it for epoch numbers. Let's say epoch is 1,000. So we only want to run it 1,000 loops each time in the total training loop. Okay. Within this total training loop, each loop also cares about the error amount. If the total error is greater than this error that you want, okay, keep doing it. Keep doing the minimization, all right, until your total error is less than the error that you set. So if my ERR error here is very big, then my training will end very fast, right? Because I'm very relaxed. I don't need it to be the error to be so small, right? Just a little bit learning is fine. I think it's learned already. If my error is set to be very small, means my requirement is very strict. I need it to minimize quite close to 0, let's say, before I am satisfied that the network has trained. Got it? Okay, so that's what this is. So for every epoch, train the network until it reaches some desired level of error. Okay, so if the error is big, it will train faster. It may not be training very accurately, but it will end faster. If the error is very, very small, it will take longer, all right, but it will be more accurate. Okay, so this is a tweak here, the hyperparameter here. Okay, then we have some other holding things like pattern error and all that. That will come in later, you'll see. Because again, we need to have some indices of the network performance. In the hot field, it was the energy and the Hamming distance, right? In here, we have things like pattern error and total error and things like that, okay? So we have a momentum term, and that's the way it's implemented. First, we create a holding pattern for the momentum, okay, because we want the previous weights, right? Remember the learning rule is the learning part, new part, plus the old momentum part. So we want a holding pattern for the old momentum part before we apply it to the new part to update the total change in weights. So this part is to prepare the momentum term, having some sort of a holding pattern here, okay? So initially, I created as an empty holding pattern, sorry, an empty m here that is multiplied by mu, which is the momentum term, which is one of the hyperparameters. Okay, so now we actually do the feed forward part. We have and again, see, I have this copy thing because this is where if you go deep into the code, you will know. If you just make whole pattern W equals to 0 whole pattern W, if you change whole pattern W, it will also change 0 whole pattern W. I don't want that. I want it to be split. So what I do is I do dot copy. Okay? So that's what this does. All right. Now we learn the change in weights for each pattern, but don't apply it yet. In other words, what we are doing is, this is called, where's my pen? This approach is what we call batch updating. We have 8 patterns, right? Category A has 2, category B has 2, C, D, each of them has 2. So total we have 8 patterns to learn, to train. We want the network to do all the categories first, all 8 patterns first, okay? Because the idea is, right now, W is whatever random state. We are saying whatever random state you are at, we want you to calculate how much you need to change in order to learn pattern 1, 2, 3, 4, 5, 6, 7, 8, relative to whatever state you have now, right? It cannot be that I have a random state, I learn pattern 1, then I change it. Then I use this change one then to learn pattern 2, and then I change it. And I use this new learn 1 to learn pattern 3, and so on and so forth. Then it's not fair to pattern 8, right? Because pattern 8, what it has to overcome is what this network has now learned from pattern 1 to 7, correct? So batch updating is a way to say, like, whatever status your network is, freeze it, learn all these different patterns you wanted to learn relative to that frozen pattern, hold all this learning information first as a batch. Then, when you have finished your sweep of all the patterns you want to learn relative to the original state as a batch, then apply those independent updates. We call it superpositions, okay, into the original pattern state. Then you can learn 1 to 8 again, and in a batch updating way again. Okay, so that's what batch updating does. So that's why we say here, don't learn it for each pattern, but don't apply it yet. Okay? All right. So then how do we learn it? Well, first we have AI, the input, and we make AI take it, we select pattern P first. So let's say we select the first pattern. For all the number of patterns we have, let's choose the first pattern. What's the first pattern? Well, first pattern is let AI be equals to the input, whatever input we had, the first vector. And now we use that first vector and we do feed forward. So we propagate the activity. So from lines 103 to 114, for every layer of whatever architecture we have, remember it's an MLP, so you might have 1, 2, 3, 4 hidden layers, however many hidden layers, and each hidden layer has different number of units. Doesn't matter, we've already set it up. So then for each layer, first we set the bias to 1. So if k is equals to 0, then we make AK equals to the input. If this is the bias, if this is, for this layer K, if it is the first layer, okay, then AK is going to be, the last unit is going to be appending the input with a 1. Otherwise, we will make this layer the last one. Okay, -1 means the last unit equals to 1. What this means is that because my input, so if I go back again, here. What this means is this. Actually, my higher, the part where I set the bias units will only, that piece of the code will only set this one. It won't set the input layer yet. Because the input layer is not part of the network. The input layer is from the stimuli. Okay? So I can only set, I only set the bias units. So let's say if I have more, then I have more bias units. So I only set these internal bias weights originally. Okay? But actually, I also need to have the bias for the inputs. So this line of code here is why I have to have a if, why I have to have a if else logical conditional is because this is to handle the input layer being fresh from the input. Then I add the bias unit, append 1 to the whatever input size. Or else, if it is the network itself, well, then it's easy. I just select that last unit that I already created and set it to 1 as well. Okay? So this is to set the bias unit of the current layer. And then I apply the logistic or the sigmoid activation function, which is that I first have a pre-activation state. So can you understand this? This is W A vector, A input. Right? MP dot of the A input times the W, right? For that layer, layer K, which is the net input. And then this net input, this is the SciPy special expit exponential function, which is the sigmoid function. Okay? This one is, just to be explicit, okay? Okay. And this one is AJ. Okay. That's all. So, and we do this for every layer. Sorry, for every pattern. We do it for every pattern. Okay? We don't apply anything yet. No, where am I? Sorry. Yeah, not pattern, layer. Yeah, sorry, didn't see that. Okay, we do it for every layer first. So we forward propagate the activity. Then we calculate the delta. All right, so then from here, let's move this up. We do the backprop, which is we create error, all right, an error vector, so like this, okay, and then we want to calculate the change in weights for the output layer and also the hidden layers differently. okay, and correspondingly, okay. So we have delta J and also the delta H's. So for delta J, output layer, okay, this is going to be delta J is equals to AJ minus AT. Nope. Right? AJ minus AT times AJ times 1 minus AJ. Can you see? I hope you can see that. Okay? So that's delta J. And then, so, and this is where pattern error comes in. It is just an index of evaluation for evaluating the model later. So if you see this, sorry, it's not delta J. It's you recognize this? Sum of squares, error, right? So it's just variance. Okay, so actually pattern error is variance, total variance. Okay, so then, yeah, then we calculate, this is eta. This part is the error and the AI. Okay? Not yet applied, just holding it, right? Okay? So that's what this line does. And this is for output layer. Delta J, calculate the weights, calculate the delta, have some, measure of the level of variance or error that we have, and then calculate some initial holding weights to change. Okay? All right. So that's all this part. Then let's move on. For hidden layers, okay, we have the same thing here where the delta H is equals to the delta J from the downstream error multiplied by the W's of the J to H, okay, multiplied by then the AJ 1 minus AJ, the derivative. Okay, that's delta H. These three parts. Okay, then similarly, you calculate the weight change. Oops, sorry, I wrote that wrong. HI is equals to eta, and then the error, delta H now, and the inputs that led to that no, I think it should be H, sorry. Yeah. Okay. That was associated with the resulting error. Okay. Then finally, because it's hidden layer, okay, so the output layer does not have a bias unit, right? The output is a 4-bit word, which is what we want, the 4-bit word. But if you are a hidden layer, you have, remember, you have the bias, right? So we do have to account for it. So we have to make the bias, it's just numerical, because otherwise there will be numbers in there. We just make it 0. It's not important. Doesn't, just nullify it. All right. So then we do this for all the patterns. All right. But then we finally sum it up. say I'm going to concatenate these, okay? HIs for pattern 1 to 8. Okay? Nope. Okay, what that does is basically sum it over all the 8 patterns for the output layers and the hidden layers, all the changes in weights that we have calculated, sum it up, then we batch add it to the actual pattern. These are holding patterns, if you want, okay? Holding patterns, okay? Hope you get the logic here. And then you do it again until you reach the error that you want. Remember? So if you go back, go back up. Do that until the total error, because you calculate the total error here. See? Calculate the total error. So you do that over and over again until the total error is whatever minimum you set. So it's a hard thing. It's a hard numerical, forcing it to be some arbitrary number. My error can be 10. It can be 0.0001. Who's to say whether 10 is better or 0.001 is better? It depends. It's something we decide what error we want, okay? But in theory, in conceptualization, okay, you know, those, we don't worry about that. Let's just say we want 0.001. Why? I don't know. It sounds like a good number. If we are okay with that, it sounds very small, okay, relative to all my, 10 bits, of errors. Then I'm okay with that. I mean, in theory, the maximum error you can get for the pattern of a 10-bit pattern is 10, right? Because when you do, if you are wrong in all 10 positions of the 10-bit word, then your maximum variance is 10. What is that, 100? If you square it. No, if you square one, it's still 10. Yeah. So the maximum is 10. So if you want your error to be less than 0.001, it means that, wow, not one is wrong, right? Okay. So that's how you can think about it. So anyway, so we do this over and over and over again until we reach some error. We are satisfied that the model is no longer making any errors. Then we return the final train weights, WT, and we also report the error that is associated with the performance of this particular instance of training, WT. Okay, so this is the training function, and this is the core, it is the heart of the backprop network. Any questions about this one? Okay, if not, then the next thing is, so we set up the training function, and now we want to define the next function, which is the testing function, okay? And this is very easy. Basically, it's just the feed forward, the feed forward part of the training function, but without bias. Because all we want to do is we test it. We're not worried, we're not going to update the weights. We're just going to use the weights. So we're not worried about explosion, or we don't have to normalize or regulate anything, okay? So actually we shouldn't be having the bias units. The bias units were not part of, they were just a way of controlling the range of the weights. But they're not actually the important contributor to the performance of the network in terms of the actual solving of the mapping solutions. So we just, for the testing function, all we need to do is set it up so that it can take the train weights the input we want and some information about the architecture. Units layer is a way to say how many units per layer, okay? And then we use the train weights and the testing input, and we see what is the output, right, based on these weights. And so we don't have biases, so we only select the non-biased weights in the train network, because the train network will have those upstream to downstream bias weights. Okay, we just don't want those. All right, so we take them out, and then we apply the logistic function to it, to the input times the weights, then put it in the logistic function, and then we get the test output, which is return A. And then we can see if A really matches AT after we've trained the network. In theory, it should, because that's how we train the network, right? Yeah, it's kind of like after a while you sit there and you think this is such a circular logic. But that's what it is, okay? All right, so then the rest of it is, you will see, is similar to the way we approach the Hopfield network, which is that, well, in order to really test this in a rigorous and systematic way, what we will ask, what happens if we distort the input patterns by some level of probability? How does the network hold up as the training deviates more and more from the original training set with some level of probability? And then we also have ways of visualizing. So we want to see some gradient descent application. So this is just a plotting visualization to take the total error and then see how the total error changes over time. And some other visualization tools. These are not so critical, but it will be for the evaluation time where we want to do more large-scale evaluations. All right, you can spend time to look at this, but maybe we will talk more about this next week in the lab session for this network. But it's just a way of visualization. Okay, the core concept has already been done in the train net and in the test net functions. All right, then this is again a visualization way. And we apply it. Let me see. Yes, these are all visualizations. Okay, so now we want to try it out. And what we're going to do here is we're going to set up the actual simulation methods now. We're going to have our input array that we want, which are the 8 input patterns. Then we have the output target array that we want, which are 8 output targets, but you can see really they are just 4 different output states. Just to match that we have 8 inputs, we want there to be 8 outputs, but actually there are only 4 different outputs, types of different outputs. We specify the hyperparameter information. So like I said, we want it to run maybe only 1,000 times max. In terms of each time it minimizes the error to 0.001. We want to do this minimization 1,000 times. And we only want it to learn at a rate of 0.3. But we want to be a bit more conservative. We don't want it to change so fast. And in fact, it should have a bit more momentum, 0.7. So what it is this network is going to, if you think of it in the search space, okay, it's going to jump a little bit at a time. Let's say it starts at some location and the solution is somewhere there. It's trying to find its way there because it could end up anywhere else. And in order to get there, it just takes 1 baby steps, 0.3 magnitude steps at each time, okay? Because where it is originally is more important, okay, than what it is learning, and then it's going to move smaller steps in order to get to the solution. If you change it any other way, eta, let's say eta is 0.7 and mu is 0.3, it will jump a lot. So it doesn't care where it was originally, it will jump very far. So you can imagine how that might play out, okay? Is if you are taking baby steps, you take longer to reach the solution, you may not even reach the solution, okay? Within 1,000 iterations. If you take big steps, you might reach the solution faster. However, you might also skip over it. Okay? So those are things to help you imagine conceptually what is happening, how these hyperparameters operate. Okay, so finally, we are ready to actually run the simulation, and this is my implementation. I'm going to train my network, so I'm going to use train net perceptron function with an initial untrained network. So I'm just going to say no input, no pre-trained W. Just make your own W from the random states, okay? Part of the train net perceptron code. The input is A, which is this, A. And the desired output is O, okay? And I want you to set up an array network that is having the architecture 10, 24, which means it's feed-forward, fully connected. It has 10 input units, 4 output units, and a hidden layer, one hidden layer with 20 units. That's what this means. And I want it to run for 1,000 epochs, and I want it to each time minimize to 0.001, and the eta and mu are 0.3 and 0.7 respectively. Okay, so train this network like this, and give me what you have. So the train network will be WT, and report the error associated with this training protocol. Okay, so then I visualize the network. So again, this visualization function comes from some of the earlier codes. Okay, so I want to visualize a 1024 kind of thing, and it looks like that. Okay, not surprising. And I train the network, and I have the total error, and I want to visualize how the error changes over 1,000 iterations, and it just does gradient descent. Okay, it becomes closer and closer to 0 over the 1,000 times it learns. Okay, if your network is performing okay, sometimes it might go up, but on a whole it goes down. Okay, but if your network is performing okay, it should always look something like that. All right, but because it depends on the first one is it depends on the original randomization, right? The randomization might be such that it's lower, and then when you train it, it would start higher. Actually, the correct way is the second iteration to start the error, but it doesn't matter, okay? So if your network is performing correctly, it should be doing gradient descent. If your network is not doing gradient descent, something's wrong with your code. You are not doing what Hinton is wanting you to do, okay? So this is one check to make sure, sort of like a troubleshooting, one troubleshooting indicator, all right? Like sometimes, yeah, I had where errors keep going up, or it just stays still, it doesn't change. You know it's not doing what it's supposed to do, okay? So this is really ideally what we want, something that just keeps going down, and then asymptotes, settles on some level, it doesn't really change anymore for many, many, many times, okay? So, and then we test it on distorted patterns. So I'm going to test perceptron that is trained, okay, WT now. And then I'm going to give it input pattern 3, okay, and I specify that, the architecture is 1024, and I see that here. The input pattern is 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. Which one is this? It's pattern A3, which is 0, 1, 2, 3. This one, right? Yeah. Okay, row 6. Okay, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0. So it's row 6. Row 6 should be associated with 1, 2, 0, 0. No, wait, row 6 should be 1, 2, 3, 4. So row 6 should be this one. Okay, row 16 is the output. So it should be 0, 1, 0, 0, correct? Okay, see what's my output here? Okay, close to it, because the weights are random uniform. It's float, it's not integer. This is not hot field where it is regularized, binary regularized linear unit. So it's not, the output is never going to be exactly 0 and exactly 1. But you can see it's very close. Okay? So then I can test it in other patterns, but it will basically be something like that, all right? So it will be for every pattern that you give it to test, and depending on how much distortion you do, it will approach the desired output in the float sense, not the binary sense. So there will always be some error, right? Because it's not exactly zeros and ones, but the error will be very, very close to zeros. Yeah. Okay, so that's how it works. Any questions about this? Good. Yeah. Yes. Yes. Which one? Test train net? Okay. Yes. Forward. Yeah, so after you do the forward propagation, right? Then, and then you do the back prop, right? Then we calculate here, total error, which is the sum of the pattern errors. And each pattern has an error. Where's the pattern error? Here. This line. Yeah. Yes, this one. Yeah, and then we keep going, right? Yes. But there's no bigger than the error. Then we keep going, not smaller. Sorry. Yeah. Bigger than error. Yeah. But there's no smaller one. Like if the total error is smaller than error. If it's smaller, then we stop. Then we stop. But there's no line. No line. There's no this line in the function. If works that way, right? If it is bigger, right? Keep going. If it is smaller, then don't do anything. What you're saying is that else. You need an else. Yeah, you need an else. In this case, you don't. If the error, as long as the error is greater, keep going. I guess it's sort of like a while. You can think of it as kind of like a while. But if it is greater, then do this. If it is smaller, don't do anything. In fact, if it is smaller, then just make go to the next epoch. Go to the outer loop, in which the outer loop is loop over t range. So t is going to be, let's say epoch is 1000, right? Yeah. Okay, so I'm going to start, let's say t is 0. All right, the first time I do t is 0, correct? So in other words, t is going to be from 0 to 999, okay? So let's say t is 0 now, and my total error is bigger than error, okay? So if total error is bigger than error, is that true? Yes, it is, right? Okay, so I do all of that, and I see, is total error bigger than error? Still, so I do all that again. Is it still bigger than error? Yes, I do all that again. And then now, is total error bigger than error? No, nothing. So then, go back to t is now 1. Get it? And then, look at the total error because it is now a new epoch, then I do it again. And I do it again, and I do it again. So when will it stop? Huh? So it will stop at 1000. When I have done this, each time I do this minimization of the error to be less than error, I will do this 1000 times. That's why you see my, here. it will always be, this plot will always have 1,000. Will always have 1,000. I can say I want to do it 2,000 times. Then this will have 2,000. Yeah. So what you're saying is because, yes, it's sort of like a while t is greater than, while the error is greater than error, well, the total error is greater than error, keep doing this, right? And then if it is not, then go up, then come out of this loop. Then do whatever, but that whatever makes you go back into the loop again and do it again. So that's how these two loops are working.
Okay,
Yeah.
And for example,
Yeah.
I think the chance is very unlikely. But
Yeah.
For example,
Yeah.
the random weight that the system inputs
Yeah.
has already a smaller.
In the first time, right?
Yeah, in the first time.
Yeah, so then if it is in the first time, yes, I see, the probability is very, very low. But if the first time is done that, then it will just do it 1,000 times, like without even looping too much. It will still do 1,000 times because I required t to do 1,000 epochs as a hard rule. I didn't have any conditional for the outer loop, right? This is a for loop. So it will have to do it 1,000 times. And if each time the error is already less than 0, then that means this computer will only run 1,000 computations or 1,000 iterations. But more likely, the W will be such that the error will not always be less than error. So it will actually run more loops than 1,000 because it will run as many loops as it requires to reduce the error to be less than error 1,000 times. Yeah.
So in that unlikely case,
Yeah. That is less than, yeah.
It will still do
Yeah, 1,000 times.
The W will never be updated, right? Because the W will only
It depends. No, it will still be updated. Oh, yeah, you're right. Yeah, because it will never go into that loop. Yeah,
it
correct.
will never go into the if.
Correct. Yes, exactly. Yes. But then, in terms of the problem, it solved the problem, right? If your W, if your pattern error is already 0, what do you want me to minimize anymore? There's nothing to minimize.
So the return WT would still be just W in that case.
Correct.
Okay.
Correct. Yes. Okay? Make sense? Okay. Yeah, great question. So I mean, these different things, this is just it's an engineering solution. I said Hinton's way is more of an engineering way of doing this. It's sophisticated, yeah, but I mean, I don't know. You can have your comments and your, like, what if, does this break it? Does this really mean what it is? There's room for debate and questioning. So it's similarly, now I have a LLM. Now we have ChatGPT. And we say, oh, ChatGPT, we want it to become perfect, right? We keep training it so that it becomes more and more like it really learns what we want it to do. But if by some weird random chance, ChatGPT, you use a random and you make a ChatGPT that randomly exactly already performs like a human in terms of language, then there's nothing to train ChatGPT. It's already performing, what language. So and if that happens, then what does that say about, the gradient descent and all the neural network and all that? Well, it just shows that there's some random chance, there's a random chance that intelligence could appear without any prior training. That is chance, okay? So there's implications there, right? Yeah, that's what that would mean. And how does that make us understand how things work? Well, I don't know. So those are the problems, sort of like, is it helpful to frame the problem this way? Or maybe it is, and what does that mean about intelligence? Yeah. So if some random thing, intelligence pop up in the universe, will you call it intelligence? I guess. That is the moral question. Right? Essentially, that's equivalent to that problem. If I did random thing, and then my network randomly, I don't need to reduce any more error, is equivalent to, in the whole universe, by chance, there was a chat GPT that was perfect. Would you call that intelligent? How do you reconcile that with your existence? Okay. I'm okay with that. I think that makes sense. So. Any other questions? Oh, and feel free that if you guys are, going through the assignments, and then as you do the basic stuff, applying it from the ground up, and then you all want to expand and explore, and then you use AI to help you build models and other models with, constraints. As long as you understand what you're doing, and you explain also to me that I understand what you're doing, actually I'll be very curious to see, hey, other ways of solving that is very reasonable, that is well thought out, that is very well argued. I'd be very curious to see, how other ways of solving or identifying problems with these original formulations. This is the way that Hinton did it. Okay? And this was back then when they started it. I'm sure right now, they've advanced beyond that. But does that negate these initial proof of concepts right from the start? Yes or no, right? Those are all legitimate questions. The qualification is that if you do that, then you have to make sure that you are not so-called cheating, in a sense that, of course, if you use PyTorch or TensorFlow and all that, then they will have all these complicated things that will solve things in a different way. The question is, do you understand what they're doing? And does it make sense, right? Is it fair to what we are trying to do here at the more fundamental basic level without using tools, engineering tools, more from a conceptual ground-up development, okay? So more mathematical, if you want to put it that way. Okay, so let me finish for today, and then maybe we can end early, is that after you have, we've tested this initial training, and we've even done it on the distorted pattern, here are some questions to think about, okay? So take a look at how the MLP performs, okay, and retrieving target outputs based on actual and distorted inputs. So that's that's part of the assignment, actually, okay? So what do you think? Do you think that it fulfills a nonlinear mapping problem that we set out? How can you prove that those are nonlinear mappings? Or are they actually still linear mappings? Okay? So it's very tricky, okay? In the single layer perceptron problem that we set out, we just had 2 inputs and 1 output. So logic tables and OR problem, very straightforward. And then when we break it, because we give it an XOR pattern, it couldn't do it. So we know very clearly one was linear, then the next one was nonlinear. Because it's just 2 units, very easy to visualize linearity of the problem. Here you have a 10-bit word. In a 10-bit word mapping to a 4-bit word, how do you know that that mapping is linear or nonlinear? Okay, so you can think about that. So therefore, if that's the case, this training really proves that you can map anything to anything. Or is it still just doing linear mapping? And actually, if you give it nonlinear mapping, actually it couldn't do it. Okay? So think about that. It could be that, yeah, so what's your argument? You think that it still does, and you can show your case, yeah. Or maybe it doesn't. Or maybe you don't know. You say, we can't know, okay? All right, so that's to get you thinking deeper about this, okay? We won't deal with it today. We might come back to this in the lab next week, all right? But this is something to get you thinking beyond just what we talked about today. And then also, obviously, are there other visualization? We've just do some basic visualization. Are there other visualizations you think might be helpful? Like for example, you want to look at the heat map of the weights. You want to see how the weights change and all that very cool stuff, you know. Yeah, I think visualization itself is also a very cool track to go, because sometimes with visualization, you see things about how things work that, you know, it's very hard to think just abstractly or in terms of numbers. You can see things visually, sometimes it will enhance your evaluation. Okay, so these are some things to think about. We won't deal with these other things, like for example, simulation 2, then we will think about, because your Hopfield network was doing auto-encoding. And then here we say you're doing mapping anything to anything. Well, auto-encoding is mapping something to itself. So it is within the set of mapping anything to anything. So which means that theoretically, the MLP can also do auto-encoding, right? So how do you do that? Okay, how would you implement that? So again, something to push you beyond the basic range of stuff. So I've done that. So I have some visualizations and all that. I won't go through that today. I'll do that in the lab next week. But that's where we are at for today, for now. Okay, so that's backprop MLP in terms of the theory from last week, and in terms of the coding applications this week. And then so next week we will be, you have the assignments, I've made it open. Assignment 2 is open. And we will be dealing with that, launching you into assignment 2 so that you can deal with it, all right? And then through all this whole exercise is to demonstrate to you now what delta learning backpropagation means and why it works the way it's said it's supposed to work, why it does what it's supposed to do, okay? Of course, feel free to disagree and challenge it and say why maybe it doesn't work, or okay, it works what it does what's supposed to do, but that's not really what we want still, or whatever. Okay, we will come back to these things maybe later on. All right, any final notes or queries? Yeah, sure. Mm-hmm. Yeah. The difference between these two networks? Excellent question. And there's two ways to do it. The first obvious way is, well, try it out yourself. You have a Hopfield network. You have a backprop. Give them the same data table and see, right? I mean, that's an exciting project. That's an exciting simulation to run. And be rigorous about it. It's not like you just do it simply and then you make, try to tweak it and do all sorts of, get at it from different angles, and then you find, hey, does it perform better or worse, or why does it perform better or worse, and all that. That's a great question. So that's the first set of answers you can try. So try it out and see how it goes. From a conceptual point of view, my take on it is that they are trying to achieve different things from the start. So when you say better or worse, it depends on what you are trying to evaluate. Okay. The backprop is trying to minimize error. So whereas the Hopfield is trying to represent memory, is trying to encode and stabilize information. This is related, but not exactly the same thing, or even subsets, complete subsets of each other. I would argue they are in orthogonal directions. Why? One is trying to maintain itself. Like whatever I am now, please remember it as much as possible and don't deviate too much. In fact, if you deviate, then you have forgotten yourself, right? And that's the Hopfield. One is, whatever you are right now, that's not important. You could be right or wrong. So if I tell you you're wrong, you should change yourself. Yeah. So you see, from a conceptual point of view, they are having two different goals. The interesting thing is, So for me, conceptually, there are different goals. But so the interesting thing would be, is there a conceptual way to frame it such that, no, actually they're still the same goal. It just depends on what you mean by error and what you mean by self. I don't know. At that point, my brain gets into knots. And I just stuck at this place where, no, I still think that there are different goals. So is it better or worse? Well, then it depends. Is your goal trying to maintain itself, or is your goal trying to consume error, trying to learn from novelty? And I would then argue that if your goal is trying to remember, perhaps I would suggest the hot fuel is better. If your goal is trying to learn new things, then actually maybe the backprop is better. In practice now, actually, you will see that there's nothing to stop you from combining these two into one big monster of a network. You can have parts of your network that remembers itself and parts of the network that learns from new things. And I would argue actually that's what your brain does. Yeah, that's what our brain is. It's remembering some parts of itself, but also being sensitive to its changes in the environment. So it's a very intriguing question. Okay, so the two ways to suggest to answer it is to actually try it out from a more engineering computational point of view. Another way is more philosophical, I guess. So you think about it from a conceptual point of view, like what does that even mean to say, are they better or not? Yeah. Thank you for that question. That's really great. Yeah. Actually, I was thinking, like, I've always thought about this for this course, is we have three networks, right? We have the hot field, the backprop, and later on you will see the unsupervised learning. I was always like, is there a way to challenge it? I don't know, it might be too difficult, I don't know. But after learning all these three, can we have an assignment 4 where you try to combine all of that into one monster network? And then create your own problem, combine it, and play with it, have fun, and see what it does. I think that is actually what we really want to do in the end. But I mean, short of time, that might be a semester 2 thing. But so like after you learn these three, then combine it into higher level networks. At least for this course, basically, just at least get past these three basic ones. It's already quite enough. Yeah. I argue that if you did that, if you combine these two, at least if you did a hot field and then you do MLP, and then you incorporate some elements of the unsupervised learning part, you actually get a brain. At least that's what our brain is doing. The complexity that is there. Yeah. Any other questions? I have one question. Where do you think the error is? You all talk about the delta, right? To train the network. And we always talk about neural plausibility, right? Here, at least here we talk about neural plausibility, biological plausibility. Where is error coming from? But that's the question. We have delta, we have error that we use to train the network, right? Right? In biology, what is this? Yeah. Oh, great, yes. You have to have some sort of a prediction, isn't it? Yeah. In this implementation, Hinton doesn't talk anything about prediction, right? They are all just saying something where we have some desired output, some target output. Only then, when you have that, then you can talk about error. Yeah. But they never go back to say, well, biologically, where does this desire or target come from? So, but when you say prediction, how does that actually work? When we predict, what are we predicting? So let's assume that, okay, maybe let's consider that error comes from, we have a predicted output, and therefore we have an actual output, and then therefore we have an error. Okay, all right. So then there is a prediction. Let's assume that there is a prediction. What is this prediction? What are we predicting? Or what is the biological system predicting?
Based on the Bayesian cognitive model,
Uh-huh.
human or any cognitive creature body can absorb all the perception and
Yeah.
try to predict what will be
What would be?
next, like what happens later.
Okay, so yes, so let me rephrase that, and I do agree. I think, so the prediction is about what, so the input is this sensation, and actually the prediction is about what's the next sensation, right? Okay, so the prediction is about the next sensation. So the prediction is actually about what's the input, right? But here the error is based on the difference relative to the output. So different, right? It's different. I think it's close, but there needs to be some tweaking, that the target is actually about input, not about output. Because in our biological system, there is, even if you want to say my output is I press a button, the target is not about I pressed the wrong button per se, but that I had the sensation of pressing the wrong button, right? That my motor, and then my visual, and then the outcome, which is about input, not about output per se. So at least the strongest source of error for us is about the input, not so much about the output, right? So think about that. So then how would you tweak the model? Because this is, right now all LLMs are actually trained this way. It is about output, not about input. Well, as far as I know, I mean, maybe secretly they've already changed it, I don't know. But in terms of the fundamentals that we are told about, right, the principle is still always about that. It produces some predictive text. This text is what humans produce. So how different are the LLMs to the human production? And so adjust the LLM based on that. But it is not about the sensory of like the inputs themselves, right? So it's very close, but be careful. It's not exactly the same. Then when we talk about biological systems, it's not about output, right? It's about input. Yeah. So think about that. I think that's also another very under considered field, range of questions. Yeah, to this day. I don't think it's hard to tweak the model to actually fit it. It's just that it's very funny is that I haven't seen people really think about that too much. Yeah. And I would also argue that part of the input is actually not just the sensation, but your hot field self is part of the input. So it's what we are predicting is not so much about what will happen later, but what we feel like that we would experience later. So we are part of the next prediction actually. This kind of very, very deep, but the sense, the prediction is not just about the outer world. It is also about we as part of the outer world, ourselves as part of the outer world, right? And then we are making our changes based on this Bayesian prior, actually. Yeah. Yeah, this Bayesian expectation. And then we get the actual evidence of what happened to us in the outer world. And then we integrate or combine that to say, okay, then what's our next prediction about what's going to happen? Yeah, something like that. Okay. Anyway, a lot of things to think about. It's very exciting actually to me, and it's always an ongoing research question, I think. So if people are interested in this kind of work, I'm always up to talk more about it. Okay? We can keep talking and talking, and it's never ending. And then, but we have to put a stop because we have to focus on the class. So for today, I think we can end early. We can end here. And then next week, we'll be doing the lab format again. So next week, please come prepared to be like, again, everyone set up the screens or sharing things, and then like we're gonna try out the questions, and then share with each one how you do it, what difficulties you encounter, and we'll try to implement the code and all that. Okay? All right. Okay, so thanks, and we'll see you next week. Remember, next week though, hot field assignment is due, so please finish your hot field assignments. And you can, if you finished, please submit it if you haven't already. If you haven't, then done, you're great. If not, please make sure you submit your hot field assignments next week, by next week. Okay? All right, and then we can then turn to the next backprop assignment. All right, thank you.